Palestra da Rohde Schwarz, nosso patrocinador de diamante, que desde já agradeço a todo o apoio que os senhores têm dado desde fevereiro, que a gente está conversando com os senhores. Então, muito obrigado por patrocinar o nosso evento. E, a partir de agora, passo a palavra, ele já falou, vai se apresentar, ao senhor Schultz, que vai se apresentar agora. Muito obrigado.
Thank you, Major Augusto. Hopefully I pronounced that correctly. As the Major said, my name is Walt Schulte. I'm a product planner for Rohde and Schwarz. And so a product planner decides what features and performance go into the next generation of our instruments. In this case, I mostly plan the signal generators and signal analyzers. The signal generators are what we use for electronic warfare simulation. As the Major said, I've been in test and measurement for about 12 years. And then prior to that, I worked for NavAir, which is the civilian government arm of the United States Navy. We did the acquisitions and testing of electronic warfare systems. So I have a background testing radar warning receivers, jammers, and yeah, maybe I should switch to that. So I have a background testing radar warning receivers and jammers for self-protection, mostly for our F-18s. Then prior to that, I worked for a company that's now a part of Raytheon on some remote sensing problems. Then I was in the U.S. Navy serving as an officer on a ship in San Diego before that. So there's a LinkedIn profile in the program, and that links to my father, not me. So yeah, just be aware of that. The link on the program does not link to me. I am Walt Schulte III, and I did not name any of my sons after me because it just gets too confusing and makes the paperwork a mess. So yeah. Today we're going to talk about EW environment generation. And so here's the agenda. First, we're going to say, what is electronic warfare? You guys, we have a lot of pilots or people in the Air Force in the audience. You guys probably know what this is, but we do have a mixed audience online. So I want to ensure that everybody knows what we're talking about. Then how do we test it? Basically by creating an EW environment. And then we're going to get into more of the fine details on testing, scenario generation and building environments from models of emitters and so forth. Okay. Just real briefly, I want to give a background on how this whole field or science came to exist. Back in the 1970s, the United States was fighting a war in Vietnam, and we didn't have air dominance back then. We got a lot of our aircraft shot down in air-to-air combat at first. Finally, we solved that problem. We built better aircraft. We put a gun back on our aircraft, on our fighter aircraft, and so forth. And then after that, 90% of our aircraft shot down were shot down by surface-to-air missile systems. So that's how the Navy got into electronic warfare. We're detecting and jamming these surface-to-air missile systems, and that's why it's so important today. So by electronic warfare, there's a couple different terms that you'll see thrown around often. Electronic attack, and that typically means like jamming, and that can be done with high power at a great distance with one of these pods underneath an aircraft. You might have seen the E-18G Growler that has, radiates megawatts or gigawatts of power. There's also electronic support, and then that might be passive intercept and location of an enemy radar signal. A lot of times that comes with recording as well. They might be recording this signal to later use it in testing. And then electronic protection, that protects allied systems from enemy electronic attack. These are often features built into radar systems. For example, ultra-low side lobe levels built into an air defense radar would be a form of electronic protection. And also just ensuring that you're not radiating any unwanted signals, EMI, or just controlling your emissions. So when we talk about electronic warfare, the pilot, and this is kind of an old display, but the pilot is really concerned about being shot down by an air defense system. So he wants to know where all these air defense systems are on the ground, what modes they might be operating in. Are they in a search mode, or are they in a tracking and a fire control mode? A tracking and a fire control is a much bigger problem for the pilot. That means that the air defense system is about to try to shoot him down. And so the EW system, in this case, we mostly mean a radar warning receiver, is going to measure and categorize all the pulses coming from all of these radars out in the environment. And you can see that they're in many different bands. These radars are all the way down to VHF. And then you'll have the search and acquisition radars up in L and S band. Embraer makes these. And then you have these tracking and fire control radars up in X band all the way through KU band. And then the missile seekers themselves tend to be, even higher than that, a multiple of that. And so the EW system has to measure all that in the environment and display to the pilot where all those threatening radars are out in the environment. Okay, so that's what we're talking about when we talk about testing this, trying to recreate this environment here. And so I just got into this. This kind of proceeds from simple to complex. So threat simulation, these air defense systems are called threats. Why? Because they threaten to shoot down the pilot. So what we're trying to do is simulate these threats at RF ultimately, and then inject them into the electronic warfare system and see if the electronic warfare system can detect them. And then we're going to do that in increasing levels of complexity. Why? Because the environment is very complex. There's millions of pulses coming in per second on this radar warning receiver at all these different angles. Okay. And then on top of that, we might start adding all the communications emitters, which, as every new wireless standard is closer and closer to a radar band. So we have to ensure that the electronic warfare system can distinguish between a radar and a communication emitter. And then there's all kinds of other signals out there, friendly and enemy, that you might add to the simulation. So I didn't create this graphic here. This is a U.S. government graphic. But, the reason we want to simulate is the alternatives are kind of test during combat. So we tried that in the 1960s. Gary Powers flew a U-2 over a new SA-2 air defense system in Russia. And that didn't go very well. So that's one way of testing, the hard way. Another way of testing is to do flight testing. You put all these emitters out on a flight test range and you fly around them. The problems with that is that, at least in the United States, this has to be scheduled months or years in advance. It's not very repeatable, and it costs, millions of dollars an hour, or, more after the inflation of the recent years. I've been told I'm live streaming, so I need to not say anything that goes viral. But yeah, so it's just really expensive, unsecure. Anybody who has a receiver can pull up next to the range if they have a sensitive receiver and listen to what's being radiated on the range. And then if you find something wrong, well, you have to go fly again. Simulation, on the other hand, is very finite and scalable and repeatable. You're simulating out of a signal generator, and you can get the exact same result every time. You can scale based on the cost and complexity of the simulation you're trying to create. It's precisely, and it costs a lot less money. So the United States is trying to go more and more to just simulating in the lab, and I know the UK has done that as well. But they're trying to do that by increasing the fidelity and complexity of the simulations they do in the lab, so they're more and more like a flight test range, but cost a lot less. So when you're simulating, there's a ton of things that go into it. It starts with institutional knowledge. Why are we doing this? Well, I described the history of electronic warfare at the very beginning. We're doing this because air defense systems are a big threat to pilots, and they're everywhere. They're relatively inexpensive compared to, putting a bunch of aircraft on a carrier and sailing over and getting them all shot down. So they're kind of a force multiplier for any country that has good air defense systems. So that institutional knowledge is like built into the bottom of this pyramid here. Why are we doing this? Okay. Then the next thing is, well, we have to collect information on all these air defense systems so that we can simulate them. So that involves electronic intelligence, flying past an enemy country and trying to collect the signals that they're radiating out of their radars. And then you have to figure out how to build the EW system to detect all that. So I'm going to show a mixed architecture EW system that I made up, but there's a lot of different ways to do this. And there's all these engineering trade-offs, and building an EW system that's affordable and effective and lightweight to put it in a fighter aircraft or a strike aircraft or a bomber. And then from there, you need to start through the test process and test all of it, and then ultimately hope that it works in theater or in the campaign, right? And that theater or campaign is going to be different depending upon the geography, the country, and the radars they have. So this is just a mixed architecture EW system I made up, but this is kind of how a lot of them are designed. They're there's incoming pulses from the threat or the enemy radar, and these are all parameterized into digital pulse descriptor words or waveform descriptor words, and then that might be a 64-bit representation or digital word that describes things like the angle of arrival that pulse came from, the frequency it's at, the pulse width, the time of arrival, and the amplitude. Often there's modulation on pulse, like linear FM chirps. And then millions of these are coming in per second, like 5 to 10 million of these are coming in per second, depending upon the altitude, the range, the effective radiated power of the radar, the sensitivity of the EW system, all sorts of things. So all those have to be sorted out into one radar there or the other radar over there. And then once they're sorted out, the system needs to track what mode it's in. Is it in a search mode or a fire control mode or something like that? And then the tracker sends feedback to the sorter to try to keep pulses from that same threat out of the sorting process to reduce the computational load. Okay. So now you're getting a sense of like how we might start to test this, right? It goes from very simple to very complex. And as I'm going to explain, down here, you might start jamming the radar, or you might talk to a standoff jammer that might do it on your behalf. So you might also take the RF from this pulse and use it to make a jamming technique. Okay. So one of the key sorting parameters used that I showed here is the angle of arrival of the pulse coming in. And why is that a key sorting parameter? It's because as you're flying, the angle or the relative bearing to the radar on the ground changes the slowest. So it makes it the best thing to sort one emitter out from another. So the older systems, as depicted here, and I'm not saying that there are no more advanced systems on this. I'm just saying this is an example of an old system. It's doing amplitude comparison monopulse direction finding. So it's got these receive beams oriented at look angles of 90 degrees relative to one another, and it takes the ratio of the amplitude of these two pulses, the arctangent of that ratio, and it says that emitter is at that angle of arrival over there. The newer ones do that, and they do, they compare the phase between ports on the aircraft. They do what's called interferometry, and that typically gets you almost an order of magnitude more precision in angle of arrival. And they might also do time difference of arrival, but you can see that there's, apertures all around this aircraft. There's, and to test this thing in a full 360 degree azimuth, you're going to need test assets all around this that connect into the ports on the aircraft or the system under test to give a full 360 degree test of the system with the ports that the DUT is using. And so you can see that just from one generation to the next, the level of complexity in testing has increased. So this starts to suggest a test and evaluation plan, but basically the idea is you're going to test, one emitter. Make sure the system can identify the waveforms, and then once you know that you can do that, you might see that I can identify multiple emitters at a time. Then you might start putting geolocation on those emitters that you're simulating, and then angle of arrival. And the more complexity you add, the more realism you add to the simulation and the test process, but the more difficult it becomes, particularly when you're doing angle of arrival. There's a huge calibration task that is pretty difficult. It's a task we've solved it as a company, but flight testing, ironically, makes that a lot easier, that form of testing easier, and that's why they do it. But then after that whole test cycle, you decide, is it ready to go or not? So now we're going to get into EW simulation. This time we're going to start with a better graphic than I had at first. So the first thing you're going to do is collect electronic intelligence on the threat, and then you're going to figure out, what waveforms this threat is using, the pulse width, the modulation on pulse, the PRF, and then the antenna scans and so forth. And then you're just going to inject those one at a time into the EW system. And you might call this mission data file testing. And this is the simplest form of testing. And you're typically going to do that by building a model up of this threat and trying to collect intelligence on as many of these different modes in this threat as possible so that you can identify these modes one at a time, okay? So that's the start of kind of like modeling for EW simulation, and it's also the start of testing at the same time. I went over this, but, again, it starts kind of with the pulses, the sequences, the antenna pattern, the antenna scan, and then you're just adding complexity on that emitter from there. But as you add complexity, you're making this emitter more realistic as you inject it into the system under test. And when you make it more realistic, you can have more confidence that the system under test can handle it in the real world. So I covered this. These are kind of some graphical displays you might see as you're building up a model of an emitter, and what you might do, as you're preparing this emitter for injection into the system under test. So the waveform, I kind of covered this, but there's a variety of ways to create the waveforms for testing. You can just create an IQ waveform, which is a complex number fully describing the signal you're trying to create out of the signal generator. It's very precise. It's the exact waveform. But the problem is these files tend to be large. So you're using a lot of memory inside a signal generator to create one. Okay. And if you're trying to create millions of these per second to simulate in a realistic electronic environment, then this is the wrong tool to use unless you've preloaded all these. Then the other thing you can use are what are called pulse descriptor words. And I already showed those in the electronic warfare system, but you can use the same concept simulating an electronic environment. You can take a 64-bit or so forth parameterized description of the pulse, its time of arrival, its amplitude, modulation on pulse, and so forth, which is much smaller than an IQ waveform. And this is something you can send millions of per second to simulate a realistic electronic environment. Very data efficient. And this is typically where you're going to head as you're going to add complexity and realism to your simulation. Yeah, so this is an example of an antenna scan. This would be like or something a tracking radar would do when it's tracking a sector or volume of space, looking for enemy fighters and deciding which one it's going to shoot down, right? This first level, though, really what you're going to see in the testing when you're just simulating the antenna beam pattern, the scan, is the system under test is just going to see power scaling, okay? The scaling of the power relative to its simulated position relative to the simulated threat, okay? So that's kind of like the next level of complexity beyond just testing the waveform itself. What this ends up doing is decreasing the probability that the system under test is going to intercept this threat. Why? Because there's like a scan-on-scan problem. So that's why these systems are typically designed to receive at all aspects and as many elevation, as much elevation as possible all the time, so that it avoids this scan-on-scan problem between the EW receiver receive beams and the radar threat beam. Then you can start putting these emitters and your SUT on a simulated map. And so you can make that map static, or you can, give it a track. This would be another level of complexity you could add to the simulation. You can start scaling the power not only by the beam pattern and scan, but also the range, and also the effective radiated power of the emitter you're creating. It's another way of looking at that. You can put it on a map. Then you can start adding platform motion. So instead of static simulations, you can start putting Doppler on top of it. And you can add more dynamism to the emitter you're creating. You can add mode changes. As this aircraft gets closer to these other aircraft, these aircraft are going to change modes, maybe from search mode to a tracking mode to a fire control mode. So that's all going to change according to where these are relative to one another on the map, okay? And maybe instead of just simulating one, I'm simulating all of these at a time, okay? That is realistic, right? Typically aircraft don't fly by themselves, but in ship, 2 ships, 3 ships, squadrons, so forth. So that's another layer of realism, but also complexity you're going to add to the simulation. So this is where you start having a lot of problems. And there's a huge trade-off between, several variables. How realistic do you want to make the simulation? How much money and space do you have to buy equipment to make it realistic? And what do you do? There's not infinite money or space to just keep buying equipment to add realism to the simulation. So you have to make trade-offs. You have to decide, if I'm going to, how many pulses I'm going to simulate from how many emitters at one time, And all that kind of translates into how much pulse on pulse I can create versus how many pulses I have to drop. How many pulses can I play versus how many pulses can I drop, right? So this is a huge factor in both the realism and complexity of the simulation you're creating. So typically what you see is you start seeing, multiple RF sources combined into ports on the system under test. And there's, you can combine these out RF, or you can combine these emitters back in the digital system and then send them out of the same RF port. But what ends up happening is you have to combine resources into ports on the SUT to increase realism. And that makes for a cost problem, a calibration problem, and ultimately a test time problem and a complexity problem. But it all has to be compared to flight testing, which is the most expensive, time-consuming way of testing. So that's why, despite the complexity of doing this, EW engineers still do it. And then, finally, one of the most important levels of realism, but also the hardest to test, is testing the angle of arrival. And as I said in the very beginning, angle of arrival is a primary sorting parameter of these EW systems because it changes very slowly and it's very useful for distinguishing one threat from another. So it's a really important thing to test. And as these systems have become more advanced and more complex, testing angle of arrival has become harder as well. You've got to calibrate the amplitude, phase, and time between the signal generators you're injecting into the ports on the system under test. And the calibration tends to be, after you've created the right signal generator, the calibration is the hardest problem. So we can talk more about that afterward. I've got an entirely different presentation on that, which I can talk for a long period of time. But yeah, this is like probably the last thing you're going to do, and also the most important and the hardest problem to solve. And then again, you're not just doing one emitter at a time. Why? Because the EW system is seeing maybe thousands of emitters at one time with millions of pulses per second. So now you're not only calibrating the ports creating one emitter, but also multiple, right? And then, the challenge is doing all of that for a realistic period of time. Why? Because, it takes time for an aircraft to fly a mission, right? He has to launch from a runway or a carrier, fly toward the air defense system, hopefully blow it up, and then fly back. And so I've never flown one of those. I don't know how long that takes, but it can take tens of minutes to hours, right? And so to do a realistic simulation, you have to be creating all these emitters with all that pulse on pulse with the angle of arrival for tens of minutes or hours, okay? And then keeping that calibration stable for that entire period of time to ensure that the whole thing was realistic. And typically what happens what you do for these simulations is you're starting with the model of these emitters. You have a really powerful computer. It's computing, what it is trying to simulate these emitters in software, and then there's a digital system that creates these emitters in an FPGA and then sends these pulse descriptor words out to the signal generators, at a rate of millions per second. Okay, and then they're doing that for tens of minutes to hours. Okay, and then that's probably like the highest level of realism you can achieve when you're testing in the lab. So, there's several different ways of testing in the lab. A lot of times they just get the receiver out and put it on a bench and connect directly up into it. Then they might combine multiple signal generator ports into ports on the SUT in order to increase that pulse density and complexity of the simulation. Then you might have multiple SUTs you're testing at the same time to test cooperative EW, right? Multi-ship communication and electronic warfare. So that's kind of like simpler bench testing. You can also cable everything up to the SUT, while it's still in the aircraft. So a lot of times, I showed this earlier, but there will be apertures positioned around the aircraft, and you can take those apertures off and replace them with adapter plates and connect the signal generator directly up into it that way. Or you can radiate over the air into a chamber, and typically if you're going to do this, you're also going to do that, okay? This is nice because the angle of arrival is created by the position of the standard gain horn or the reflector around the aircraft. You don't have such a phase, amplitude, and time calibration problem because you're creating the angle of arrival by radiating over the air. Yeah. Often you want to check this against this. And again, this is all compared to flight testing. There's only so many chambers. But again, you don't actually need a chamber. Often you can just connect the signal generator up to the SUT on a bench. But it's scalable. It does multi-emitter simulation. It's flexible. It's secure. You're not radiating out of the chamber as long as you looked for the emissions coming out of the chamber and then sealed up any gaps in your anechoic material. And I think one of the best things is it's repeatable. You can do the same thing over and over again. It's very deterministic. Okay, whereas flight range testing is not. There's a high upfront cost in equipment, but again, compared to flight testing, you're paying for manpower, you're paying for fixing the airplane, scheduling ahead of time, the jet fuel, all that. So it's almost like you can pay for all the test equipment in one flight test. Yeah, I think I've covered calibration, covered all that. I covered the benefits over the air. Again, one of the main benefits is that you're creating angle of arrival by the physical position of the antenna radiating down into the chamber. So it's less of a calibration problem. There's still some, but it's much less. And this gives you more confidence in the angle of arrival measurements your EW receiver is doing. Yeah, I think I covered all this. So I've tried to make the case here for EW simulation, how important it is, not only to ensure system performance, but ultimately it's important to the pilot. We're trying to keep the pilot alive here. There's a ton of institutional knowledge that goes into all this, and a ton of supporting activities that need to be done, such as electronic intelligence collection, building up intelligence databases, and all that ultimately goes into the test stimulus that are done with increasing levels of complexity to ensure that the system performs as specified. What we're seeing is less and less testing being done over the flight test range for a variety of reasons. Cost is a huge one. And at this time, I can take questions. I'm pretty much done. And we do have some gift bags here for anybody who does have any questions. Go ahead.
Good afternoon. I'm Professor Marcelo Souza from INPE. I worked with modeling simulation for many different things, and recently I had a doctoral student working in some aspect of this. jamming, etc., etc. But my question is more different, more focused on the question with model and simulations is always how the fidelity of the model. Since you are testing, recreating enemy air defense systems, how do you know how you model the enemy's defense systems, especially their characteristics, electronics, etc., etc., etc. And later, this is the question, model fidelity. And the second is about how you choose simulations, the cases of simulations, 1,000, 10,000, 1 million, to be representative. So with models, the question is fidelity. With simulations, the question is sampling the space, the infinite space of simulation. So could you briefly comment on that?
Yeah, I think you should probably give part 2 of this presentation. But yeah, the fidelity is a very, very tricky question because it relies on the fidelity of the ELINT receiver collecting the intelligence in the first place, right? How good is it? Then the analyst interpreting that electronic intelligence and then putting it into a test. And ultimately, you don't know. You do have other data that tells you what kind of air defense systems a country has, right? But maybe you haven't seen their wartime modes before, right? I think one of the things is, you've got identify friend or foe. You know where you are, and you know based on the angle of arrival and geolocation where that other signal is coming from, and if it's more likely to be an enemy or friendly just based on its geography, right? I think this is where this starts getting into cognitive EW. AI is a term thrown around a lot nowadays, but you can kind of infer based on the pulse repetition frequency, the geolocation, the center frequency of the emitter, and so forth, whether it's an enemy or not. Just based on that information. Is it in a fire control mode? Is it in a fire control band? Then it's probably not friendly if it's like pointing it at you. But the fidelity of the fidelity of the simulation needed to positively identify that threat versus the fidelity to say, oh, that threat is probably harmful are two different things, right? You just really need to know, is it harmful? Is it pointing at me? And I need to simulate to that level. And so maybe you need a cognitive system that goes, oh, this looks like a pulse Doppler fire control mode coming from that direction over there, which is known to be in an enemy territory. I'm going to simulate to that level, even if I can't perfectly recreate the emitter's analog characteristics and all the other stuff gathered from electronic intelligence. So that's my view on the first part. That's the second part is that kind of answers the second part of the question also, but how do you know how much to simulate? I think you can infer from the effective radiated powers of the emitters, what altitude you're going to be at, the terrain, and other intelligence you gathered on the country's air defense systems to try to create a more realistic scenario based on the performance parameters of the SUD, mainly the sensitivity in a given band, and be like, all right, well, I'm at this altitude. I'm probably going to see this number of emitters at a time based on their effective radiated power. That's what I'm going to try to simulate. But that's where I would start the process. You like that answer? Okay. Yeah. So I'll give you the bag afterward. Go ahead.
And first of all, congratulations for your lecture. And I'm a specialist in the electronic warfare, and it's very clear for me this kind of test based on the equipment and the simulation itself. But how you are face the challenge of this kind of scenario in data fusion approach? I mean, in the aircraft, they have more sensors that combine it and give the pilots the final response to do that job.
Yeah, so that can actually make the problem worse, not better. Data fusion. I think you want to try to create as simple of a receiver as possible, but not simpler. You have optical systems, to detect infrared from a launched missile. From our point of view, a lot of times that's too late. Like it's too late when they launch the missile. Now you're getting out the tow decoy or something like that, or taking evasive maneuvers, which burn a lot of fuel. Then there's other receivers on board the aircraft that maybe were made by different manufacturers. And so how well do those talk to one another? If it were me designing the radar warning receiver, I would make sure that all the functionality is just in one instrument, and I would only perceive the threat modes based on RF alone. Now, you can detect launch based on the infrared, and you should, right? So that would be the only other fusion I would try to consider. What you hear a lot of talk about nowadays is kind of like a knowledge-aided cognitive approach, where you take information you already know about the country you're flying against and somehow build that into the cognition of the EW system, so you know what's more likely to be seen. And that's another way you can fuse more information in. But in general, I don't think it's a good idea to have too much data fusion. So I'm on a broadcast here, and I'm not going to say any more than that, but, talk to me afterward, because I don't want to say anything that goes viral, okay? But, yeah.
I did not vote. Voted? Se não temos dúvidas, muito obrigado pela apresentação. Thank you very much for your presentation.
Sure.
Agradeço mais uma vez a empresa Rohde Schwarz pelo patrocínio, pela ajuda nos últimos anos. Foram vários anos aí de eventos conosco. Então, muito obrigado. The gift, can I give it?
Sure. Please.
E, é claro, uma salva de palmas para os nossos palestrantes, por favor.